Thanks. So next we have Ernesto De Matteis. Will be virtual.
Okay. Good afternoon. So to everybody, can you hear me?
Yes, we can.
Okay. I think that you can see also my presentation. So in sharing mode. And okay, so thank you. So thank you to Yota for the opportunity and everybody. So for the workshop and today I will speak about the superconducting magnets for advanced gantries and with on behalf of my colleagues from INFN LASA, my home institute from of Milan, and Eurosig, ITRIPAS, and IFAST project that are the subject at the end of the project mentioned in my presentation. About the hadron therapy, so okay, you already know better than me that what are the main scope. What we can say, so just for introducing superconducting magnet, that the depth at the end of the Bragg peak depend strictly on the particle and on its energy. And in particular, if we saw at the end the graph here on the right, so the carbon ion are higher energy with respect to the proton, and the use and now from our idea also in the ITRIPAS project at the end is to explore at the end the possibility to use carbon ion and that are more effective for tumors that are resistant to traditional therapy and products, but for due to this energy at the end they are limited for the sites and the cost of the needed infrastructure. About the dimension of the medical facility for the carbon ion, so and depend strictly on the magnetic field of this of the magnet. And already as Maurizio in his talk of this morning, so already mentioned that if we try to use at the end to substitute normal conducting magnet that are limited to Tesla. We try to apply at the end superconducting magnet, so increasing the magnetic field, we can reduce of a factor at least to the dimension and the footprint at the end of a medical facility, of an accelerator, and that it means so cost reduction and also possibly to reduce also the power consumption on the long term of this kind of facility. Looking the gantries, they are our target for the presentation. We can see that for the protons, so at the end the gantry already used, so particularly the rotatable gantry are already compact. So on the market we can find several companies working on this. So they are making compact this kind of gantry. For heavy ion, for carbon ions, we can find just 3 of these of the rotatable gantry. The unique in Europe is from Heidelberg. We can see on the left bottom. That is very huge, based on normal conducting magnet, and the other 2 based on superconducting magnet in Japan. So we can see from built by Toshiba, and we can see from the dimension how they reduce a lot the dimension and the weight using just a superconducting magnet. So our Japanese colleague, they started almost 20 years ago with the concept, with the study to apply superconducting magnets. So now our target is to use, so to study the same at the end, to introduce in Europe the superconducting magnet technology. So here we I mentioned at the end that the EU initiative in the last 6 years, started mainly by CERN. We can find two different concepts. One is based on gatoroid and will be the topic of the next talk given by Ariel Laziot. And the second concept, at the end, more classical gantry, at the end, or rotatable gantry based on superconducting magnets, SIGRUM. At the end, designed by Terra in collaboration with CERN. At the end of 2020, so there was a review about these two design, and the final decision was to explore at the end more in detail the rotatable gantry that was linked as more ready at the end from the technological point of view as a final decision, and then in any case to continue the study on the gatoroid, a completely new design for this kind of machine. Then in 2021, there was the setting up of the 3+ and the IFAS projects, and both the projects with one work package dedicated on superconducting magnets that focused mainly for accelerator and gantry, mainly based on CCT dipole, so candidate cosine theta dipole. And in 2022, the setting up of one INFN called the SIG, so superconducting ion gantry, then was integrated in the European SIG agreement, focused on a study of a rotatable superconducting gantry based in this case on a curved cosine theta magnet, so a different layout magnet. From this, so 4 years ago, at the end, we started the discussion. We fixed the parameter of our target. So how to have an ion therapy gantry. So from this, so we started from the beam rigidity of the carbon ion, 6.6 Tesla meter. And from this, at the end, we decided our superconducting magnet target. So the 4 Tesla dipole, a curvature radius of 1.65 meter. And then a ramping rate of 0.4 Tesla per second that is needed to optimize at the end the treatment of a gantry. And that is one of the challenge at the end, the curvature radius and the ramping rate. At the end, the main advantage is, okay, it's clear at the end to reduce the weight and the cost. Then the main disadvantage is the need at the end of a cryogenic system that without no liquid helium, because at the end also for the gantry for the operation we don't like. So at the end, another challenge is the cryogenic system. Starting from this overview at the end of the 3 project, so I introduced SIG and the EuroSIG initiative. So the SIG is a call INFN that then was inserted in the so-called 4-party agreement, INFN, CERN, CNAO, and MedAustron, for the development of the key technology for an ion gantry. And here we can see at the end on the right part, at the end, a rendering of approximately, so the main structure at the end of the gantry. And starting from the same parameter that I mentioned before, in order to reduce, for instance, the weight of this gantry and the dimension. Then the key technology to develop in this, so the main target was to develop the 4 Tesla curved superconducting dipole, the scanning magnet, the dose delivery system, and the range verification system. So the four target from the technology. And looking at the end the complexity of this magnet with respect to the curvature radius, we can see that is very complex, also comparing to the classical accelerator magnet. About the superconducting magnets, so that we are developing here at LASA, in particular my colleague Marco Prioli is in charge for this. So the main objective at the end is to develop a curved cosine theta. So based on cosine theta coils that are the standard layout used also for the LHC dipole. based on an IO-Buntai superconducting Rutherford cable. So for Tesla magnet, 80 millimeter of bore diameter, curvature radius 1.65 meter to reach at the end our beam rigidity. The high feed ramp rate at the end is one of the challenge with the curvature radius, and then the cooling system. At the end, the idea is to study a conduction cooling system, so without liquid helium. Then all the targets, so at the end, conceptual design done, also a review, and as we can see here on the right, so there is a rendering of the final magnet, and on the bottom right, we can see the starting of the winding of the curved coil. As we can see, so very a lot of tooling that we need for this, so a complex procedure. About the E3 Plus, so we have the work package 8. At that time, I have the honor to coordinate this superconducting magnet design. On this, at the end, the three main scope was this one. So we started with the study of various magnet design. So we studied also cosine theta and canted cosine theta layout with different superconductor. Then we decided to explore a curved CCT layout. And here we can see a reconstruction with the magnetic flux on the bottom right, based on IO-Buntai, so a rope 6+1, with the same, exactly the same parameter that we fixed for all the project at the end, all the that we are speaking. Then the main is the construction of and the test of a small demonstrator based on this layout. Just the status at the end, just looking at few detail of this. At the end, the magnet is based on a rope. At the end, an industrial cable 6+1 with copper, and here we can see the layout in the groove to generate at the end the 4 Tesla dipole in the bore, 2x7 rope. The main parameter is the ramping at the end of the between 0.2 0.4 Tesla per second, and we will test it at the end in liquid helium. For the moment, this kind of test. We performed already test of winding for straight geometry, and we launched at the end the production of the most critical part. This the curved former at the end. The curved, so it means the mandrel, the structure for the conductor. And here we can see the final, the end rendering of the final magnet. The idea at the end is to have the demonstrator, final demonstrator at the beginning of next year, very challenging, and then to perform a test in order to have feedback from this kind of magnet. Then the IFAS work package 8. In this case, so the IFAS, so we have innovative superconducting magnet. Here the scope was a little bit different, so we focus always on the same parameter, but on straight demonstrator. Here the main scope was to study at the end the application of a HTS magnet for accelerator, and we focus on the medical application. Then at the end, the two main scope at the end.
I'm sorry, but you have to sum up in like.
Okay. Sorry. So the two demonstrator, one on the LTS, one on the HTS. Here, very briefly, so we have exactly the same structure of the curved one. We have just a combined function. So is the important feature at the end to be tested for a CCT to have dipole and quadrupole, a corrector. But mainly we have the same conductor. For the HTS, we have a 4 Tesla dipole based on Repco tape, so a very challenging R&D in this case. So we have a cable like this with 2 HTS and the copper, and very interesting because here we have a company that is collaborating in this in charge for the final demonstrator. Also another experience for this kind of magnet. And one of the things to verify at the end is the efficiency of this kind of magnet in a conduction cooling, because the operational temperature will be 20 Kelvin instead of 4.5 Kelvin in order to have an efficiency 5 times higher. So in conclusion, so I show at the end what is at the end the superconducting magnet role. So we can have a more compact medical accelerator and in particular gantry. The project as EuroSig, Gantry Plus, and IFAS are important for us, to start to learn at the end to face the main challenging that are useful for implementing a gantry, a superconducting gantry. In particular, also the integration with high temperature superconductor is the future at the end in terms of superconductor. Both the layout they can improve at the end the strength of magnetic field and also to give feedback for gantries and accelerate. Yes, finally, so yeah, at the end, so just still, so we need to face the main challenges that are the cryogenic system, the ramping rate, and the AC losses for the medical application that we never face at the end in a normal accelerator. Thanks for the attention. I'm ready, so if there are any questions.
Thank you, Ernesto. Any questions?
So, using the new superconducting magnets, when we can expect a real gantry built with these magnets? Do you have some realistic estimation? And if we compare the new gantry with what we have, for example, in Japan, could you compare?
Yes, no, a good question, because it's something that we are started to discuss also with our colleague and our partners. And at the end, looking at the experience of the Japanese colleagues, so they have 15 years above us, so they already faced our technological issue, and I think is reasonable. So we can a little bit speed up, but I think in 10 years. So 10 years could be a reasonable time to have a final design and also a sort of industrialized gantry like this.
Thank you.
I also have a question. I've read that the researches are being made in finding superconductors that have superconducting properties in room temperature. Do you think it's possible to find such superconductors? And if so, would that exterminate any negative when using superconductors?
Sorry, but I didn't hear very well. So, so the sound is not so good. Could you repeat, please?
Yes. I've read papers that are trying to find superconductors that have properties in room temperature. You don't need the cryo to superconductors need a low temperature.
Sorry, but I didn't hear. So the audio is very bad. So I didn't get it.
It's okay.
Okay, we'll go ahead and move on.
Yes.
Let's move on. Our next presentation is Innovative Gantry Designs
Okay.
Continue
Okay.
with